Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Contest alert. This week we have a jam-packed intro, including a new contest we're launching, so please bear with me. You don't want to miss this one. First, a bit about this week's shows. As you may know, I spent a few days at CES earlier this month. While there, I spoke with a bunch of folks applying AI in the consumer electronics industry, and I'm including you in those conversations via this series of shows. Stay tuned as we explore some of the very cool ways that machine learning and AI are being used to enhance our everyday lives. This includes work being done at Anki, who built Cosmo, the cutest little computer vision powered robot. Lighthouse, whose smart home security camera combines 3D sensing with deep learning and NLP. Intel, who's using the single-shot multi-box image detection algorithm to personalize video feeds for the Ferrari Challenge North America. Firstbeat, a company whose machine learning algorithms analyze your heartbeat data to provide personalized insights into stress, exercise, and sleep patterns. Reality AI and Koito, who have partnered to bring machine learning-based adaptive driving beams or automatically adjusting high beams to the US. And last but not least, Ariel.ai, who applies sophisticated analytics to Wi-Fi signals to enable some really interesting home automation and healthcare applications. Now, as if 6 amazing interviews wasn't enough, a few of these companies have been so kind as to provide us with products for you, the TWIML community. In keeping with the theme of this series, our contest will be a little different this time. To enter, we want to hear from you about the role AI is playing in your home and personal life and where you see it going. Just head on over to twimlai.com/myaicontest, fire up your webcam or smartphone camera, and tell us your story in 2 minutes or less. We'll post the videos to YouTube, and the video with the most likes wins their choice of great prizes, including an Anki Cosmo, a Lighthouse smart home camera, and more. Submissions will be taken until February 11th, and voting will remain open until February 18th. Good luck. Before we dive into today's show, I'd like to thank our friends at Intel AI for their continued support of this podcast. Intel was extremely active at this year's CES, with a bunch of AI, autonomous driving, and VR-related announcements. One of the more interesting partnerships they announced was a collaboration with the Ferrari Challenge North America race series. Along with the folks at Ferrari Challenge, Intel AI aspires to make the race viewing experience more personalized by using deep computer vision to detect and monitor individual race cars via camera feeds and allow viewers to choose the specific car's feeds that they'd like to watch. You'll learn much more about this application in today's show, which features Intel's Keller Emile Chin-Dickey. Andy is a deep learning data scientist at Intel, and Emile Chin-Dickey is Senior Manager of Marketing Partnerships at the company. In this show, Emile gives us a high-level overview of the Ferrari Challenge partnership and the goals of the collaboration. Andy and I then dive into the various machine learning aspects of this project, including how the training data was collected, the techniques they used to perform fine-grained object detection in the video streams, how they built the analytics platform, some of their remaining challenges, and more. And now, on to the show. All right, everyone, we are here at CES, and I have the pleasure of being seated with Andy Keller, who is a deep learning data scientist at Intel, and Emile Chin-Dickey, who is a Senior Manager of Marketing Partnerships at Intel. And we've got an opportunity to chat about one of the cool announcements that was made. Was it yesterday or today? It was kind of announced yesterday and then kind of more fully announced today. I'm going to keep you in suspense for just a little bit longer and actually ask these guys to introduce themselves, and then we'll get into what that announcement was. So why don't we start with you, Andy?
Yeah, thanks for having me. So I'm a deep learning data scientist at Intel. I started at Nirvana before the acquisition,
Okay.
working as an intern, doing some of the same kind of object localization stuff that we're using for this soon-to-be announced project. Specifically, I was implementing some other models like Faster RCNN.
Like what?
Faster RCNN.
Okay.
More recently, I've moved to kind of more similar work that I did for my master's at UCSD, which is natural language processing and dialogue systems and question answer systems.
Okay.
And so now I'm started full time after finishing my degree and
Nice.
love being here.
Awesome. Awesome. Emile?
My name's Emile Chin-Dickey. I joined last year the Artificial Intelligence Products Group at Intel, and I'm responsible for marketing partnerships. So what that means is that I work with our partner companies to showcase both partner technologies as well as Intel technologies, showcasing our efforts in artificial intelligence.
And in fact, it was one of these partnerships that Intel CEO Brian Krzanich announced at his CES keynote last night, and it's a partnership with Ferrari Racing. And I think for me, thinking back to that, to Brian's keynote, it's a little surprising for me. I guess I kind of exist in this AI bubble, and I expected it to be like just pure AI consumer devices stuff. But Intel as a company is like way more all in into this virtual reality and immersive experience that than I knew. I didn't know anything about Intel's efforts around True VR and the other virtual reality plays and the immersive experience that he talked about. I mean, and it's everything from outfitting the Olympics that are coming up. You guys built a studio, like a volumetric studio, and there was a partnership with Paramount Theaters announced. There was a ton of discussion around like how you would use this stuff in sports. And then one of the partnerships that was announced in that context was this partnership with Ferrari. So tell us a little bit about that partnership and what you're hoping to achieve with it.
Yeah, so what was announced was a 3-year partnership with Ferrari Challenge. Ferrari Challenge is a race series put on by Ferrari, and it takes place in different regions. We're specifically partnering with the North America team. So one of the areas that we're applying artificial intelligence is to the race stream. So that's basically applying AI techniques around single shot detection and fine grain classification to recognize the cars that are being captured in each of the camera feeds. And then the intent is to use that as metadata to curate camera feeds for viewers that are specific to each car or driver. So basically a fan could pick their favorite driver, and we could deliver a curated feed specific to that driver as they make their way around the entire track.
As I understand it, it's not just fans, but today like is all of the folks that are broadcasting a race like the Ferrari Challenge, they're all operating off of the same feed, like everybody gets the same feed. Is that how it's working today?
Yeah, so if you think of a traditional race broadcast, or more typical race broadcast, you have kind of a director's cut of the action. And normally the feed is focused on the first 3 or 4 cars in the race. So if your favorite driver is not among those couple cars, then you may not actually see too much of them during a broadcast. We notice that people's consumption of media is changing, and we expect that there's no reason why that shouldn't change for motorsports broadcasts as well. This basically puts more choice in the hands of the fan to kind of get a more tailored, customized viewing experience.
How would I configure my feed? Is this something that is this being delivered for me like via a live stream, and I'm choosing a car or something like that, or what's the kind of experience of tailoring the feed?
Yeah, so the intention is that this would be a stream that would be broadcast live, over an app or a website. And exactly what you said. You could pick your favorite driver and kind of get that tailored stream according to that driver.
And this isn't being done by just putting traditional cameras around the track.
Well, so there's two components. We're using drones to capture the race footage, so that actually adds a rather dramatic element to the race experience, if you will. So these are not fixed point cameras. And then the notion is that you can apply these recognition techniques to each of those camera feeds so that at any given point in time, you know exactly which cars are showing up in which camera feeds. And so with that information, you can kind of tailor that stream to a end viewer.
Interesting. And how many drones are going to be flying around the Ferrari challenge when this thing is running?
Yeah, so it's somewhat a function of the track configuration and length, but for starters, we're looking at between 5 and 6 drones, and we'll kind of go from there.
And are the drones mostly kind of fixed and each one covers an area of the track, or are they like following the cars or something?
So there's they're not fixed in one location. They have kind of more of like a territory, if you will, that they'll cover.
So you may see them like zipping around.
Yeah, they'll be moving around.
Territory.
Yeah, exactly.
Okay. I was talking to someone on your team yesterday about this at the keynote, right before the keynote, and we're going to talk a little bit about the kind of the AI elements and challenges associated with this, but just thinking about even like at this day and age, you've got to be capturing like 4K, 8K streams like off of a drone and like getting those down to someplace where you're going to process. I mean, there's a ton of stuff that, keeping the drones in the air is a challenge, but a ton of technical challenges here. Really, really interesting. So maybe this is a good segue to actually talk about some of the AI stuff. And Andy, this is where some of your work has come in.
Yeah.
Maybe tell us a little bit about kind of the underlying AI technologies and what the primary goals are for the project that you worked on.
Yeah, so we thought a good place to start. We needed a foundation on which to kind of build other analytics about all of the drivers and the racing that was going on. So we realized we needed something else to build some sort of analytics platform on. And to start that, we really needed to be able to know, okay, we're going to be using the video footage. We need to know which drivers we're looking at in any given feed, and we need to know where they are. We need to actually be able to localize them.
Right.
So obviously the first thing that makes sense is some sort of object detection or object localization model, which can draw boxes around all of the cars on the track and then potentially classify them uniquely as who's in what car. So kind of as a starting point for that, we had tested out using models that were pre-trained on some other data sets and pretty quickly realized we were going to need to gather a domain-specific data set just because, like Emile mentioned, the drone footage is dramatic in some sense, and
you don't find a lot of that out on YouTube.
Exactly.
What did you start with? What data sets did you try to train on initially?
Yeah, we were using the Kitty data set, which is kind of one of the early self-driving data sets.
Okay.
But so it has bounding boxes around all of the cars, and you can build a basic car detector off of that, but it's all from the viewpoint of kind of the dashboard of a car.
Yeah.
So some of those viewpoints apply from a drone, but a lot of our shots are really long distance and kind of unique angles that we'd never seen before in that data set.
Right.
So
right.
that was kind of our main driving factor in generating this new data set, which was a lot of the portion of the beginning of this project.
So in the typical race, you'll have these 5 or 6 drones kind of zipping around their territories, capturing data of the field is a dozen or 2 dozen cars typically.
Yeah, somewhere around there.
And for each of these drones is instrumented with a camera, and you're pulling down a feed, and you're doing what otherwise might seem like a typical autonomous driving task, like putting bounding boxes around the cars that are in the on the track. So the first step is building a model based on this Kitty data set, and then that wasn't giving you the accuracy that you're looking for, so you started building your own data set. And was this like by running drones on top of racetracks, or?
Yeah, basically. So we had a substantial amount of footage from across the entire 2017 season of recording from a bunch of drones at every single race.
Okay.
And this was in 4K. And so we knew that a lot of this footage maybe wasn't as useful. So we needed to kind of sort through that as a first step to generating a training set. So we had probably hundreds of hours of 4K footage, and it was some of the data scientist's job to actually look through and find kind of really high variance shots with differences in lighting, differences in size of the cars, since these drones will move anywhere from 10 feet off the ground to 100 feet off the ground. That really changes the appearance of the car and what the model's going to be able to learn. So we really tried to get as much variance as possible.
And what was the approach to doing that? Was this something that that was kind of manually combing through footage and hand annotating, or did you automate it in some way?
We did have some of the cut from the live broadcast that was kind of curated by the drone team that was broadcast on the stream during the race.
Okay.
So we knew a little bit of kind of what shots to follow and what was the general. I mean, obviously they're at least going to have cars in the shot if it's in the broadcast. So we were able to use those, and then some amount of manually combing through, unfortunately.
That wasn't the most exciting way that you spent time?
No.
With that, did you, the manual combing through, like what, did you use some kind of off-the-shelf tools to facilitate that? Or
luckily, we were kind of able to just write down timestamps in videos.
Okay.
And then I had written some scripts, and FFmpeg is kind of the default tool
to just snip out snippets and dump them in a drive or something like that.
Yeah. And so once we had kind of parsed through all of those and extracted some percentage of the frames, we were able to send those off to a labeling company and then provide them with a series of guidelines and kind of helpful data sheets about each of the different cars that we wanted labeled, since we had something close to 40 or 50 different cars, where some of them looked pretty similar. So it was that was kind of one of the larger challenges, was making sure the labeling team was actually able to do their job correctly, such that the model itself was able to do its job.
So how long, do you have a sense for how long you spent on just this kind of data collection and pre-labeling task?
The data collection itself, the recording of the video, was over the entire 2017 race season, so I guess that maybe shouldn't be included. But kind of the curation of what we were going to provide to them, I would say happened over a week or two.
Okay.
We were able to get a couple different data scientists looking at it, and people who...
And you started with 100 or so hours, I think you said. What was what was the size, like if you added up all the snippets that you sent on to get annotated? how many hours did you have of that?
It was close to, I think, 1 hour.
Okay.
So
So
significantly
very
less.
dense set.
Yeah.
Go
Yeah,
ahead.
we even, after that, we obviously, because from frame to frame, there's really not that much difference.
Mm-hmm.
We were pulling something like maybe 10% of the frames, so that we can get more variety with a lower number of frames,
Mm-hmm.
since it really, every single frame is more effort for the labeling team, and you're really
Mm-hmm.
trying to reduce that as much as possible.
Right. So meaning you use 10% of the frames in the 1 hour of footage. And then you had this labeled by the labeling team. I would have imagined that you needed a lot more training examples to achieve, acceptable performance on this. Were you using these examples in conjunction with the previous, was this a transfer learning type of task, or did you train from scratch with these new examples?
Yeah, we ended up actually going straight from scratch. We kind of tried to approximate the size of some of the other popular object detection data sets, like Pascal VOC.
Okay.
And so that was kind of our goal to begin with. And basically from scratch was a little bit challenging, but we realized we probably needed to do it that way just because of kind of some of the uniqueness of this problem. The fact that these cars are very small and we have 50 different classes, but they all look very similar. So it's more of a fine-grained classification problem, which a lot of these typical object detection data sets don't really cover.
And is it generally the case that for these fine-grained types of object identification problems that you need less data than, if you were training up kind of object, coarse-grained object detectors from scratch?
I don't know if I'd say less data. I think it depends on also how you develop the model. So there are some kind of future steps and kind of some of the state of the art in fine-grained detection that we're planning to implement, where you'll train a deep network and then chop off the top and add an SVM on top. And that is able to do a lot better at these tasks where the features between the two classes are very similar, but there is a boundary, versus kind of the traditional something like what we use for SSD, where it's an end-to-end neural network. So I think for the end-to-end case, you probably need about the same amount of data. We ended up having probably close to 1,000 labels per car, maybe 2,000, which seemed to be similar to some of these other data sets. Obviously, some cars were more frequent than others, and there wasn't a ton we could do besides rebalancing afterwards. But yeah, it turned out to work pretty well.
Nice.
Thankfully.
What kind of model approach, model architecture did you end up using, and how did you arrive at that?
Yeah, so we ended up using a single-shot multi-box detector, which I think Andres, who was on your show a few weeks ago talking about the NASA project, they also used that for the crater detection. So because of some of the optimizations that we have in Neon for Intel, that made sense on that front. So we were able to get kind of the live speed that we were looking for. And then also kind of the general architecture itself. It's a one-shot, not one-shot in the one-shot learning sense, but in the single-shot, like it's a single architecture. You don't have kind of a two-step process like Faster RCNN has, where first it proposes boxes and then it does the classification. This kind of happens all at once. So that is partially one of the reasons why it's significantly faster, which we liked. And it also has kind of feature maps of multiple different scales. So
what does that mean?
We have convolutional networks. When they operate and you go up in higher layers, the feature maps continue to shrink down and down further. So if we provide all of those to the end classifier, it's able to kind of get the same object at a bunch of different resolutions. So it's able to, in the end, basically it means we're able to classify objects better at a lot of different scales. So small objects, big objects, which was really one of the main challenges of this problem in this data set.
You mentioned that one of the things that you looked at or are looking at or considered was doing a network where you kind of chopped off the end of the network and replace it with an SVM. How far did you go down that path?
We haven't gotten there at all yet.
Okay.
So there's a lot of next steps that we're looking into. I'm not sure how many I can discuss, but that's definitely something we're considering.
Okay. Like, what are the kind of outstanding challenges in, trying to productionalize this? I always kind of change whether I say productize, productionalize, but
it's a production.
Yeah. So, I mean, what's remaining for you to kind of take on with this project?
Yeah, one of the big ones is the fact that the appearance of the cars isn't necessarily static in between races or even in between days of a given race. A driver may change the color of their rims on their tires, or even completely change the wrap on their car, or crash the car
on
one
some
day.
Different logos. Or...
Yeah, exactly. So if we're trying to do a purely supervised kind of one of these, like just pound it with as much data as possible to get it to learn, then that makes it a little more challenging.
Hard to keep up.
Hard to keep up. Yeah. So
how do you address that?
So there's a couple ways. The way that we're thinking to address it at this point is we would like to be able to just during practice laps, maybe take 5, 3, 4, 5 pictures of a given car. We can know when a car has changed appearance slightly. And then if we have a model that's able to learn to classify cars just based on that small support set, that would be ideal. So there's some architectures out there that are kind of attempting to do this today, and it's kind of in the one-shot, few-shot learning field. And so stuff like matching networks or some of the other meta-learning techniques, I think are what we're going to be exploring in the immediate future.
How much have you dug into that stuff so far? One-shot, few-shot, meta-learning are things that are on my list of things to dig into a bit more on the podcast this year. So if you've learned about some of this stuff already, I'd love to get a sense for, what you've seen out there and what you find interesting.
Yeah, I mean, I saw a ton of interesting meta-learning talks this year at NIPS.
Okay.
And a significant portion of them focused around kind of this few-shot learning idea. And it seems like there's a lot of different ways to approach it, and meta-learning as a framework is pretty general. And so some people were approaching it from the kind of the transfer learning perspective, where you say, okay, we're actually going to design our optimization function such that our goal is that we learn a set of parameters that with a single gradient step, we're able to achieve a variety of different tasks, or achieve high performance on a variety of different tasks, which is different than kind of just optimize for a single specific task. I think that work is called MAML out of Berkeley. And so that's something that I think is generally applicable to, obviously any model. Which is cool. And then some stuff like the matching network, where it's almost like a k-nearest neighbors type approximation of classification, where you say, okay, I'm going to give it 5 images of this type of dog and now show it a new dog, and it's going to compare with these images that it knows and see which one's the closest. And then, or do some sort of majority vote based on the class using that. So the cool thing is that they're all kind of differentiable and not necessarily related to a specific data set. So I think that makes it interesting.
So is the idea that you would have someone like at the track who is, or I guess they could be remotely, but someone who's looking at these live practice run videos and like coming up with an annotated sample and shooting that? Like, are you then triggering an entire retrain of some model? Just before the race? That sounds.
The hope is we don't have to do that. Okay. Yeah, that would be dangerous.
Yeah, that sounds dangerous.
I think we had discussed that before, and we were like, well,
what could go wrong?
What if it just doesn't finish training in time?
Right.
Yeah, so I think we want to have an interface where you can kind of just either click on the cars or draw a couple boxes around the cars. Our model will work as a general car detector from drone footage, right. Kind of regardless of how the appearance of the car changes. So it should be as simple as just clicking on the new car over a series of frames, and the boxes will already be there. Hopefully, if we use something like a matching network, those can just be cropped out and dumped into a directory, and we actually don't have to do any retraining. So the model uses those images as part of its inference procedure, which is kind of the ideal scenario.
So in what way, how is the model incorporating those images as part of the inference? So you talked about the 5 images of the dog and getting a new one. Is it these annotated car images would be presumably the 5 images of the dog, but that's happening at inference time, not training time?
Yeah, so maybe we have 5 images of every single car and associated with that as the labels. This is kind of a really rough overview of the matching network.
Sure.
They added some fancy stuff on top of this, but basically like a k-nearest neighbors. So all of those images, so maybe you have 10 different cars, so you have 50 images total. They're all embedded with some learned embedding function, or just a mapping. And then
an embedding function into what space? Like
some lower dimensional. So you just have like a fully connected neural network layer, and it goes to some smaller space. So you have now features for all of those pictures. Okay. You also do the same mapping on your new input. And then you can just compare through some distance metric or some similarity metric that new input and all of your 50 kind of just loaded images. So these images were potentially never trained on. You're really just learning that embedding function. And then once you compare and find, okay, it's closest to these 5 or these 3 or this 1, you can take a weighted combination of those classes, and then whichever class kind of has the highest vote is what you end up going with.
And how does the trained model interact with and inform the this matching process that happens at inference time? Is it that in this model the model that you've trained, the network, is only doing object detection, and then this matching process is doing the object identification? Or does having the trained model somehow inform the identification as well, but you've got this extra layer that refines it?
Yeah, so I think we could do it either way. We would like to be able to keep it as a single model, just for speed reasons. But that's still kind of in the research phase. An alternative is to kind of have the SSD model just do the object detection, and then have the whatever additional network that we have on top does kind of the few shot learning and classification of the different cars. So I think, a lot of these are things to explore in the near future.
Right. And you mentioned SSD a couple of times. What does SSD stand for?
Sorry, it's the single shot multi-box detector.
Got it. Single shot multi-box detector. Right. Okay, as opposed to your hard drive on your...
And we have an implementation of SSD that's open source on the Neon GitHub repo.
Okay.
So that's actually what we ended up using for this project. It was pretty much just plug and play with a new data set and a little bit of tuning, and we were able to achieve pretty good performance. So
nice. And now is the data set that you've, like, are you publishing this data set or anything like that?
not at this point.
Okay. Or any of the models or anything like that? Are you publishing them, or do you have like technical blog posts or something that folks can take a look at if they want to get more detail as into like how you approach this problem?
Yeah, we have a technical blog post that should be out, or will be coming out, describing some of the data collection and the modeling procedure and pre-processing steps that we used, as well as a little bit of the training. So that should give people a pretty good idea.
And are there other kind of types or classes of problem that you think that this same kind of approach would lend itself to? Or is this, like, do you think this is very custom to the unique challenges of having 6 drones flying around trying to identify, Formula racing cars or Ferrari racing cars?
Yeah, I definitely. Even today here at CES at the booth, we had a lot of people coming up and saying, oh, this could work for this sport that I participate in, or we haven't quite explored those areas in terms of partnerships or how that would work yet, but I think it's definitely applicable to all sorts of different either broadcast races or sports, or when there's a fast-moving object that it's difficult for viewers to follow, and it helps a lot to have some sort of either AI assistance or overlay or automatic broadcast control.
Mm-hmm. So Andy, this is kind of, this project was just announced here. What are some of the other things that you're working on?
Yeah, so I'm working on obviously continuing this project and some of the optimizations that I mentioned. My other work is more related, like I said, to what I had done my master's on, which is kind of end-to-end question-answer systems and dialogue systems. Using similar network topologies, if you look at it kind of squint and from a distance. Stuff like memory networks are a large part of my work.
Okay.
So I'm really interested in kind of memory augmented neural networks and the role that can play in not just question answering, but kind of a bunch of different challenges.
And are memory networks and memory augmented networks, are these related to like LSTMs and attention mechanisms and that kind of thing, or?
Yeah, very similar to attention. It's typically the memory augmented network means it has kind of some sort of fixed readable memory that you can either load items into. So for the case of the memory networks for question answering, you'll load in a story, like a text story of something that happened, and then ask it questions about that story. And so similar to attention, the memory network will kind of compare whatever its input is with all of the story that's loaded in memory. So those are very similar.
Awesome. Well, thanks so much, guys, for taking a hike over in the rain and the traffic. It was great chatting with you, and I enjoyed learning more about what you're doing with the Ferrari Challenge.
Absolutely. Thank you.
Thanks for having us.
All right, everyone, that's our show for today. Thanks so much for listening and for your continued feedback and support. Remember, for your chance to win in our AI at Home giveaway, head on over to twimlai.com/myAIcontest for complete details. For more information on Andy, Emile, or any of the topics covered in this episode, head on over to twimlai.com/talk/104. Thanks once again to Intel AI for their sponsorship of this series. To learn more about their partnership with Ferrari North America Challenge and the other things they've been up to, visit ai.intel.com. Of course, we'd be delighted to hear from you, either via a comment on the show notes page or via Twitter, directly to me at Sam Charrington or to the show at TwimmleAI. Thanks once again for listening, and catch you next time.